encoded.
May I?
Yeah. You're on, right?
Yeah, right.
Anything you want. You got your typing into the
To that console.
Yeah.
The back might be easier.
Submit. So the quick brown fox jumps over the lazy dog.
Giving it a workout.
Every alphabet. Right?
Yeah.
Every letter in the
This little
alphabet.
program we wrote is basically going to compile the text and turn it into instructions for the machine. Basically, it writes a file that we actually need to upload for the application to the machine. So this is saying that the message you wrote was 352 bits. It's going to take 59 DNA molecules to write it, so 59 transfers over here. Just going to upload this instruction.
How do you write? Again, I'm definitely
Oh, so this is
like, how do you do with these pipettes?
so this is
So the different states the DNAs are in have already been generated and put into the different wells in the plate.
Okay.
And we're just taking a subset of those and mixing them together.
it's a combinatorial encoding strategy.
Okay, so it's not like a one bit per CATG or something
No,
like that.
no.
Okay,
It's
okay.
completely different.
Okay. That's the first thing I thought of when you started presenting.
It's a very slow robot.
Yeah, it's a slow robot, and I'm actually a little nervous because we didn't. Oh, it's still working. Okay. Because it gets miscalibrated very easily. So if we're using it kind of like not that frequently, sometimes you can see it's not directly centered in that well when it took the liquid out.
You have some good eyes there.
No,
Okay, I see what you mean.
So it's
just barely.
Yeah.
Wow.
So what it's doing is it's taking combinations of DNA from these wells over here and putting them over here. But the positions in which it's placing them are prescribed by the instructions in a way that's unique for the message that you encoded.
So for that, it was 352 bits, right? It only took one sort of pipette slot? Is that the idea? Or you could store more than that in one
No, so
slot?
the whole thing is going to take the entire process. So this is going to take 59 DNA molecule transfers.
59 motions like that?
Yeah.
Okay.
So you can...
Sorry.
Yeah, I was going to say, you can think of each of these wells containing a unique molecular signature.
When you were talking about volume being the key, I mean, you store a million times more volume based on the best solid-state drives. Like, would the volume of each sort of well have to be as deep as that, or could it be smaller with the final product?
Oh, so with the final product, we're going to dry it down, so freeze dry it. So it'll be a very small pellet that you can really see.
Okay.
That's not a problem.
How did the read-write work? Like, you have to thaw it out, the pellet?
You rehydrate it, you just add a little water, and then just load it on the sequencer.
Okay. So is it more for long-term storage
Or constant
versus
storage.
rapid
Absolutely.
read-write access? Okay, that makes sense.
Things like financial data,
If you ever
medical data.
Yeah.
You ever present to a more double E crowd, like you, IEEE presentation? That's going to help if you talk like that.
It's not L1 cache.
Yeah, exactly. You got it. That's not L1 cache.
This is the YouTube
there on top of the
videos
process.
that nobody watches.
Good.
This is slower than Amazon Glacier.
Yeah.
Because Amazon.
We're trying to replace magnetic tape.
Of course, yeah. Because people use that for backup drives for long-term storage.
Right.
Yeah, that makes sense. You wowed me. That's
Yeah, but you can visualize the process.
yes, clearly, yeah.
You can imagine that.
You could do it high speed, parallelize it. Yeah, that,
Exactly.
Parallelizing is key.
So
I got
if we
that.
step
Yeah.
back- if
I'm
we
not sitting here
focus on
judging
this,
based on this.
In terms of task you take, so just take one of those, break them down into smaller bits.
Actually, just going to pause
And
it.
each bit value.
Yeah, I mean, their
That's
innovation
basically
is
the process. It's
for a subset of
combinatorial.
it.
Okay.
And if the value is 0, you don't have
Information.
value 1, you get 1.
Very
That's
nice.
right.
Very impressive.
It's much more efficient than assigning a letter to as a 1 or a
We
0.
do not have a full pipeline. Well, we don't have the.
So we can use the same
We don't
set
have
to encode
that. Is how we're gonna.
many different
That is how we're gonna create the
To
backups.
synthesize
We've
it. You have to
done
synthesize a new model.
for our KB.
I just have a question.
We don't
How
have
do you
one, though.
reduce the coding error
Yeah.
by the app information with the DNS? When you got app information with your DNS, so how do you prevent those app information to avoid like coding errors?
Apt information?
No, yeah, appin, sorry.
Hairpin.
Yeah.
So we're keeping the DNA sequences to be read out. So we're optimizing the system to be read back out using next generation sequencing. And that requires you to have about 100 to 200 base pair lengths. So it's really easy to design those pieces so that they don't contain any secondary structure.
Okay.
Yeah, we can control the DNA molecules that we're going to end up with. So we know not to include any in our library that are going to be difficult to sequence. And we can actually build them with the adapters for sequencing.
Sure. Okay. So you pre-select in fact the type of so the length of DNA that you need.
Yeah.
And so with this same set of DNA, we can encode any sort of sentence that we put in. Whereas if you're synthesizing a new piece of DNA, each time you want to encode something new, you have to synthesize it completely from scratch.
Yeah. I actually had a good analogy. So for what we were talking about before, it's like when you're designing an alphabet for a language, you're not going to assign an alphabet letter to a symbol that's really difficult to write, for example. So that's kind of like the same thing we're doing. We're optimizing the symbols everywhere. It's subjective.